All right, chemistry. This is part two of your three-part lecture for chapter 6, sections 1 and 2. In section 2, we're going to be doing a few different things. We're going to explain the relationship of between potential energy and the distance between approaching atoms, right? The atoms that are going to potentially form a bond. I want you to be able to describe the octet rule as it applies to ionic and covalent bonding. You guys are already aware of the octet rule. It's how many valence electrons an atom needs to be stable, have a noble gas electron configuration. I want you to be able to write Lewis structures to illustrate ionic and covalent bonds, and I want you to write Lewis structures for polyatomic ions and molecules with multiple bonds. Let's get started. First, a joke. You get it if you remember what a covalent bond is.
A chemical bond is the force of attraction that holds two atoms together. As independent particles, atoms are at a relatively high potential energy. Most atoms are less stable existing by themselves than when they are combined. By bonding with each other, atoms decrease in potential energy, thereby creating more stable arrangements of matter.
Now, Lady Robot really just explained the relationship between potential energy and the distance between atoms in a very, very quality and very succinct way. This is going to be information that you need to write down in your quick write, so don't be afraid to watch this particular part of the video again. But first, let's start with some vocabulary. Molecule. And molecule is a neutral group of atoms that are held together by covalent bonds. So when you say molecule, you actually need to be referring to something covalently bonded, meaning non-metals. Molecular compound. It is a chemical compound whose simplest units are molecules. Chemical formula. A chemical formula indicates the numbers of atoms and which kind of atoms are in chemical compounds, right? Not only what types of atoms, but how many of each atom is present in that chemical compound. Molecular formula shows the types and numbers of atoms combined in a single molecule of a molecular compound. And then diatomic molecule, something that we mentioned last lecture. Diatomic molecule is a molecule that contains only two atoms. Let's remind ourselves of the mnemonic that's going to help us remember the 7 elements that occur as diatomic molecules. Brinkelhoff. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. This means that referring to a sample of oxygen, you're actually referring to a sample of O2, not just O, it's O2. Now there are also 7 elements that form pure, these are also the 7 elements that form pure non-polar covalent bonds. So last lecture we said that this is actually a very rare thing, as because only 7 elements can do it when they're bonded with each other. That makes it fairly rare. Let's look at a couple of characteristics of covalent bonds. The first one that we want to look at is bond length. Bond length is the distance between two bonded atoms at their minimum potential energy. That is the average distance between two bonded atoms. And we have to remember why atoms are bonding in the first place. They're bonding to become more stable. They're bonding to create a lower energy situation. They're trying to be lower in energy. And so the lowest energy state that you can find is going to be the most supported form in nature. Okay, the lowest energy version of whatever you're looking at is going to be the version that nature supports. And so when you get two atoms close to one another, there's going to be electrostatic attraction, right? If you get too far away, okay, the attraction wants to pull you closer. If you get too close, you're going to get the nuclei too close to each other, and you're going to start to experience proton-proton repulsion. Okay, but there's this magical point where you get two atoms close to one another, and at a particular distance, potential energy is at its minimum. And because nature supports low energy situations, low energy structures, that's going to be the distance that those two atoms are at all times. The other characteristic of covalent bond is bond energy. Now, bond energy is the energy required to break a chemical bond and form neutral, isolated atoms.
Chemical bonds form when reacting atoms reach a lower potential energy when bonded than those same atoms would have as independent particles. In forming a covalent bond, electrons are shared and energy is released. The same amount of energy is needed to break them apart. This is called the bond energy. Bond energy varies with different kinds of atoms, as shown in this table.
And so this table is telling you that for a mole of hydrogen-fluorine bonds, you need 570 kilojoules to break those bonds. For carbon to fluorine, you need 552 kilojoules per mole. For oxygen to oxygen, you need 498 kilojoules per mole in order to break those bonds. So bond energy, because it's the amount of energy needed to break a covalent bond, it also represents the measure of strength of that bond. Because think about it, if it takes you a lot of energy to break a particular bond, that means that bond's pretty darn strong. So we look at the hydrogen-fluorine bond at the time, 570 kilojoules per mole required. And then at the very bottom, we have iodine-iodine bond. That's only 151 kilojoules per mole. Okay, you're looking at something like 20% of the energy is required there. That means the iodine-iodine bond is weaker because it has a smaller bond energy. So let's remind ourselves, okay, always going back to the basics here. Why do atoms bond? Well, let's remember the octet rule. By gaining, losing, or sharing electrons, each atom will have 8 electrons in its outermost energy level. Okay, we're looking at the S and P blocks here. We are not looking at the D block elements because we just don't like them. They're naughty. But when we refer to valence electrons, we are typically referring to S and P block electrons. Okay, that's why there are 8. Okay, that's why there are 8. And we also need to understand what stability is. Because why do atoms bond? We need to understand what stability is. Stability refers to atoms that have a higher potential energy when they exist alone in nature. Okay, if you just have an atom by itself, it tends to have a higher potential energy. However, nature always favors arrangements in which potential energy is minimized. This means that atoms are less stable existing by themselves than they would be when they are combined. So if there's a particular arrangement of atoms that lowers the overall amount of potential energy present, nature is going to have those atoms bond together. And like Robot Lady told us, it's going to release energy. It's going to release energy. And if you lose energy, that means that you are at a lower energy state. That makes you more stable. And nature favors that. So you're always going to form the bonds that have the lowest amount of overall potential energy. Continuing with the octet rule, chemical compounds tend to form so that each atom, by gaining, losing, or sharing electrons, okay, so we're covering ionic and covalent bonds there, has an octet of electrons in its highest occupied energy level. So whether you're going through an ionic bond or you're going through a covalent bond, gaining, losing, or sharing electrons, the ultimate goal is for you to satisfy that octet rule, okay, to gain an octet of electrons in your valence shell. This is the major driving force for why atoms bond. They all want to be just like the noble gases. They want to have a noble gas electron configuration. And so that means that they want to have a full octet of electrons. And that's why we refer to this as the octet rule, because this is what atoms want to have. This is a lower energy arrangement, and that's what nature favors. But like with any rule, there are exceptions. Okay, let's look at boron. Boron has 3 valence electrons. It's in main group 3, so it has 3 valence electrons. Therefore, it can share 3 different electrons to make bonds. That means it can make 3 different bonds. After these 3 bonds have been formed, the boron atom now has 6 valence electrons, not 8. That's because it doesn't have enough electrons in the neutral version of itself to actually, even with bonding, can't get all the way up to 8. So boron and here's an example of boron bonded with some fluorine atoms. When you count the number of electrons that surround boron, you only count 6. Fluorine, the 3 fluorine atoms here, all have 8, right? They have 8. 1, 2, 3, 4, 5, 6, 7, 8. That's fine, full octet. But boron, 1, 2, 3, 4, 5, 6. Only 6. So that's an exception. But we can go the other way. We can expand the octet rule. An expanded octet, some elements can be surrounded by more than 8 valence electrons. If they combine with highly electronegative elements such as fluorine, oxygen, and chlorine. On the periodic table, you can double check me by looking at your periodic table with electronegativity values. These are the three most electronegative elements on the periodic table. They have the highest electronegativities. So if you combine certain elements with these highly electronegative elements, this insane electronegativity of, let's use the example of fluorine. These fluorine atoms can actually be so electronegative that they reach into the d orbital, right? They actually reach below the valence shell into the d orbital to share electrons, right, to form bonds. So in these cases, it is the d orbital electrons that are involved in forming bonds in addition to the s and p orbital electrons. And so here's my example, bromine pentafluoride. There are 5 fluoride ions here, or I guess they're not ions, but fluorine atoms creating this covalent bond with bromine. There are 5 of them. Normally, we'd only think that you can form a maximum of 4 bonds, but these highly electronegative fluorine atoms have reached into the d orbital to access more electrons with which to make bonds.
The noble gas atoms are the only ones that exist readily in an isolated state in nature. The outer s and p orbitals of these elements are completely filled with electrons, 8 in most cases and 2 in the case of helium. As a result, these atoms have low potential energies and stable electron configurations. Other main group atoms can effectively fill their outermost s and p orbitals with electrons by sharing electrons through covalent bonding. In this way, each atom has a stable noble gas type structure. Let's look at this same combination of atoms using orbital notation. If we join the unfilled orbitals of 2 atoms with a box, we see that the combination fills the orbital. There are, however, some exceptions to the octet rule. The most important ones relate to the elements hydrogen and boron. Hydrogen forms compounds to share a pair of electrons, filling its s orbital. Boron has only 3 valence electrons, and so forms compounds to share 6 electrons, filling its s and 2p orbitals.
Alright guys, that's going to finish up our lecture today. So that's part 2 out of our 3-part lecture. I will see you next period.